Okay, welcome everyone. Hope you had a great spring break. Today we have Associate Professor Alexandra from CU Boulder to give us a seminar. Alexandra got her PhD from McGill in 2010, and then she stayed at NCAR actually for a while, first as an ASP postdoc, and then as a project scientist in the ocean section for 2 years before she became assistant professor at CU Boulder. And her work mainly focuses on the Arctic sea ice and more so ocean variability as well as change and also the role of ocean in the past climate. Without further ado, let's welcome today's speaker, Alexandra, and she's going to talk about the prediction of ice-free Arctic Ocean today. Thank you.
Yeah, thank you for having me, and great to be back. It's been a couple years, but nice new room you have here. Like, it doesn't look like the old main seminar room that I remember. Yeah, so excited to talk to you about predictions of an ice-free Arctic. And so I'm going to jump right in and get started, talk a little bit about the motivation why we care about an ice-free Arctic and about the Arctic sea ice loss to date. And then talk about the predictions of an ice-free Arctic, as the title said. And specifically about the impact of different definitions of an ice-free Arctic, because you might have heard about different forecasts of when the Arctic will be ice-free, but there's actually different kind of predictions that have been made, and they're all kind of referred to as ice-free Arctic. And then I'll talk about the role of internal variability uncertainty, impact of future emissions for the prediction of an ice-free Arctic, and then a quick outlook to some future needs for predictions of an ice-free Arctic. And so Arctic sea ice, so I'm mainly a modeler, but I did get to go and see Arctic sea ice during my PhD one time in September, which is the seasonal minimum, so there wasn't a whole lot left. This is in northern Baffin Bay, but at least I got to see some sea ice, and so it gets to be featured in all my talks. So it's not just model results, but all of the rest will now be model results. Except maybe this is actually based on satellite data, and that's the seasonal cycle of the Arctic sea ice. And so the picture just now was from the seasonal minimum in September, and we have the seasonal maximum in March, and this is how that looks spatially. So in March, sea ice extends outside of the Arctic Ocean. In September, it's limited to just the Arctic Ocean. And that's something you probably might have heard of. I think something that isn't quite appreciated enough is how huge the seasonal cycle is. Between the maximum and the minimum in the Arctic, the seasonal cycle is about 9.6 million square kilometers. And so that's almost the size of the entire United States in terms of area. So that's as much sea ice as we melt every year as part of the seasonal cycle and then grow again during the growth season. And this really huge seasonal cycle, one of the largest that we have in the climate system, is due to the very large seasonal cycle in the solar radiation in the Arctic, where we switch between polar night north of the Arctic Circle to polar day during the summer, back to polar night. And so the seasonal maximum is reached at the end of the polar night when the sun comes back to more and more of the Arctic. And then the minimum occurs when the sunlight decreases and we get into the polar night, and that starts off the growth season. And that's something that is still happening under climate change. But what's superimposed on that seasonal cycle is that we see a decline in sea ice area or sea ice extent, and I'll explain the difference in a minute, in all months of the year. So this is showing the seasonal sea ice extent going back to 1979 when the continuous satellite observations of sea ice started with the dark colors, and then the yellow-green colors are the more recent years. And we can see that in all months of the year, without fault, we see less sea ice now than we had in the 1980s and 1990s. And the record minimum is the dashed red line here, and we see that that specifically stands out in 2012, and so that's been the record minimum to date. We also see that in September, it's not just the seasonal minimum, but it's also the months where we've seen the largest loss of sea ice, and that's one of the reasons why we tend to always first look at September when we look at Arctic sea ice, because that's where we see the largest losses, and in a way, it kind of integrates the changes that are happening throughout the year in the Arctic sea ice. If we have less growth during the wintertime, we start from a lower point. Even if we had an average melt season, we would have less sea ice in September. But if we have a reduced growth season due to more ocean heat in the ocean. It takes longer to lose back to the atmosphere before the ice growth can start, and then we have more melt during the summer. Then we get even less September sea ice. So September kind of is integrating the changes that are happening throughout the year, and that's where we're seeing the largest changes. If we look at that over time, we can see that we've had a very clear decline in the September sea ice over time, but we also see a lot of ups and downs, a lot of internal variability. The maximum loss that we've seen between the beginning of the satellite record and 2012 is about 3.5 million square kilometer, and that's about more than half than the sea ice that used to be there in September. And we can see that that's kind of the start of this transition from a white Arctic to a blue Arctic. We're about halfway there. In 79, the Arctic, even in September, was primarily still covered by sea ice, with just some open water areas here in the Pacific Arctic, whereas in September, half of the Arctic was no longer covered by sea ice, with only the other half still remaining to be covered by ice. And again, this loss that we've already seen is quite large, 3.5 million square kilometer. That's equal to all of these states that are colored in here red. So a very large area that in the summertime, when we have this very large solar radiation, not just in September, but in the months before, we also already have lost a lot. We have a lot more radiative fluxes into the ocean that used to be reflected and now are being absorbed into the ocean, into the climate system. And so this loss of sea ice is forced. It's well outside of any kind of long-term internal variability, and that's been shown in many papers that they're on the long time scale, not a year-to-year, but 20-year average time scale. We see a very clear relationship between the September sea ice area and the global temperature increase, both in the observations, so the black and here the blue dots, and then in different climate models. Similarly, we also see a linear relationship with the September sea ice area and the cumulative CO2 emissions that are ultimately driving the global temperature increase. And the models show quite some spread, and there's really a large spread for sea ice, but they all show this near linear relationship. And so they all agree that if we have more CO2 emissions, more warming globally, there will be less sea ice. And Arctic sea ice has really been the canary in the coal mine of climate change. It was one of the first parts of the climate system where we could very clearly detect the anthropogenic influence on the climate system because it was such a large change. It's very quickly responding to the anthropogenic forcing, and so it was outside of variability very early on, and so it was kind of the canary in the coal mine of climate change. So all this talk about how Arctic sea ice has been going down, but then the last record minimum was in 2012, which is now over a decade ago. So why hasn't there been any more loss since 2012? We've actually had a zero trend and extend a very small positive trend in sea ice area, especially since the global temperatures and CO2 emissions have continued to increase, and the global temperatures in particular have hit several record new highs in the last 10 years. And the answer is that this is driven by internal variability. And back in 2011, when I was here at NCAR and Jen K was also here at NCAR, we actually had a paper with Jen, Marika, and me and JRL where we looked at the 6-member ensemble at the time from the CCSM4 and looked at the possibility of 10-year trends and 20-year trends in sea ice under historical simulations in blue, pre-industrial in black, and future simulation in red. And the probability of trends in Arctic sea ice area. And we can see that for 10-year trends, while it is more likely that the trends are negative, we can very easily have 10-year trends that are actually positive, not just zero. However, when we go towards 20-year trends, there's still a small possibility based on the CCSM4, but it's much, much reduced. And so 10, 12-year trends, as we've seen, actually weren't unexpected. We kind of saw that in the CCSM4 back in 2011. And so there's been several papers since that have kind of shown that this is driven by internal variability that is opposing the forced loss over the last decade. And so eventually, the forced response will take over again when internal variability changes into its opposite phase and points in the same direction as this forced response. And so what does that mean for the future of Arctic sea ice? So all models, even though we have a huge spread, as is shown by the shading here from the IPCC, they all agree that sea ice will continue to increase. And if we look at ensemble means from individual large ensembles or the CMIP6 models in general, we don't see any pauses in that forced response. That's really just something that we can see in the internal variability. However, sea ice is a little bit different than a lot of other climate variables like temperature. Eventually, we get to a zero bound, so we can't continue to lose sea ice at a certain point. So that's kind of what I'm going to talk about. And specifically, I'm going to talk about this line that is not actually at zero, but called practically ice-free, but usually just called ice-free. And so I'm going to talk about predictions of an ice-free Arctic based on several papers throughout the last couple years. The most recent one, which was a review article, was Marika and Jahn that came out a couple of weeks ago. So what is this ice-free Arctic? And so as I showed you earlier, at the beginning of the satellite record and prior to that, the Arctic, even in the summertime, was primarily covered by sea ice. So we had perennial sea ice cover in the Arctic. And people also call that the white Arctic, because the Arctic Ocean was primarily white. And then ice-free Arctic looks basically like this, where we now have a blue Arctic, where the sea ice goes away in the summertime. It still comes back in the wintertime. We need much, much higher CO2 concentration than will happen this century to prevent that, because the sun will still go down. And so it still gets pretty cold. But in the summertime, we actually are getting close to a potentially practically ice-free Arctic. And that's this regime shift from perennial sea ice cover, where we have sea ice that's more than 1 year old, to an Arctic Ocean that's dominated by just first-year ice that hasn't survived a melt season and won't survive a melt season. And it's nothing really magical happens at when specifically all the ice goes away. There's no green flash that happens and suddenly everything changes. It's a very gradual transition. A lot of the impacts that an ice-free Arctic will have are already happening right now and are going to continue to increase as we're transitioning towards an ice-free Arctic. But this transition itself towards an ice-free Arctic is really something that's captured the public's attention because it is such a visual example of climate change, changing especially this very pristine Arctic environment from this white ice-covered Arctic to open ocean is a very kind of captivating threshold, similar to when we passed the 400 parts per million CO2 in the atmosphere a couple of years ago. Now to the practically ice-free, so 1 million square kilometer of ice remaining. That's what this looks like. So at that point, most of the Arctic is ice-free for most impacts. And we only have ice left in the Canadian Arctic archipelago and right north of Greenland, which has also been called the last sea ice refuge. And so if this last 1 million square kilometer actually persists, it can be a refuge for ice-dependent species like polar bear to potentially survive when the rest of the Arctic Ocean loses its sea ice. And so because most of the Arctic Ocean in terms of shipping and also the impact on the ecosystem is ice-free at 1 million square kilometer, that's why 1 million square kilometer kind of has been used to determine this practically ice-free Arctic Ocean. And so in the following, I'll just be saying ice-free. So why does an ice-free Arctic matter? So it matters a lot for the ecosystems in the Arctic. Several of them are very dependent on sea ice, and they're different from ecosystems in other oceans. So polar bears have kind of become one of the prime kind of examples of sea ice-dependent species. But there's also other ones. And as we know, once we disturb these kind of ecosystem on one end, that always leads to effects that cascade through the ecosystem, even if certain animals maybe aren't actually themselves affected by the loss of the sea ice. The kind of disturbance to the ecosystem has big impacts on the whole stability of the ecosystem. It matters for the people that live in the Arctic, that depend on subsistence hunting of these species in the Arctic, as well as depend on sea ice for travel between communities. Polar bears matters for shipping. So there's several shipping routes through the Arctic, and the most popular is the transpolar sea route, because their ships can stay primarily in international waters rather than having to be escorted through the Russian waters or go through the narrow channels through the Canadian waters. And when we have an ice-free Arctic, you can see that obviously you could go through the central Arctic and stay primarily in international waters all the way to Bering Strait. Then in terms of the climate system, there's lots of impact. What happens in the Arctic doesn't just stay in the Arctic. All this extra radiation that's being absorbed during the summertime has an effect on the global radiation balance, and changing ocean as well as atmospheric heat fluxes into the Arctic with potential to lead to big disturbances in those fluxes and ultimately weather patterns. And also by opening up more of the ocean, the waves can get higher, there's larger fetch, and so the coast used to be pretty protected when there was sea ice all year round, and now the waves have been getting bigger, and so we've already seen a lot of increase in coastal erosion in the Arctic. Several communities have already had to be relocated, and several more will have to be relocated, some potentially a second time, to account for the expected coastal erosion with a longer open water season in the Arctic. And so since it matters, there's been many different studies on an ice-free Arctic. And unfortunately, which really became clear to me when we were writing this review paper, trying to kind of bring all these different studies together, many different definitions of an ice-free Arctic have been used. And that has impact on the projections of when the ice-free Arctic will first occur. And so just a quick run through. So the first time the monthly mean sea ice area extent is less than this 1 million square kilometer threshold is one that's been used. Then averaged, so the 5-year running mean of the monthly mean sea ice area or extent. When the monthly mean sea ice area extent stays below 1 million square kilometer in consecutive Septembers for 5 consecutive years. Longer term running averages, 10 to 20 years. Ensemble means that go below the 1 million square kilometer, either from large ensembles or multi-model ensembles. And then prior to 2009, the first time the sea ice extent actually reaches 0, which is still not 0 sea ice. There would still be a little bit of sea ice, but much less sea ice than this 1 million square kilometer. And we can kind of group these into 3 different categories of what they actually predict. This first one is predicting the first time ice-free conditions happen in the monthly mean. These later ones that are looking at some kind of smoothed sea ice evolution look at consistently ice-free conditions based more on the forced response rather than kind of influenced by internal variability. And so after consistently ice-free conditions are first reached, it's more likely than not that the Arctic would be ice-free in coming years in the same months. And then the no ice kind of definition. And the effect of that, I just wanted to quickly show in one ensemble member from the CSM1 large ensemble. So we see the monthly mean here in red, and the first time that goes below the 1 million square kilometer is in 2038. If we look at the 5-year smoothed one, which is the orange one, that first crosses that 1 million square kilometers in 2047. And so about a decade later, and these are these consistently ice-free conditions, and you can see that afterwards they do stay below the ice-free conditions unless the forcing reverses. After that, more likely than not, they will stay, sea ice stays below 1 million square kilometer, and then the actual no more ice when the ice extent actually reaches 0. That's another 3 decades after when we reach consistently ice-free conditions. And so there's been studies that kind of just said ice-free, but they use these 3 different definitions, and so there's been quite a wide range. Initially, this definition was used, so the early predictions were usually by the end of the century, which is still, even based on this, kind of what we're seeing. And then it moved forward to middle century because people started looking at less than 1 million square kilometer, which does happen 3-4 decades earlier than no ice-free condition. And so definitions really matter, and it's kind of important of what we're actually predicting because they're predicting different states in the Arctic, and so they're all valid. It's just kind of important to actually make clear what is being predicted. And this is not just happening in this one ensemble member, but we can look at all the CMIP6 models that have a decent performance in terms of Arctic sea ice, and we can see this clear offset between first ice-free conditions and then this cluster of consistently ice-free conditions, which don't all go ice-free in the exact same year, depending on how much you smooth them, but they kind of have that clear offset to just using the monthly mean. The other thing I mentioned was sea ice extent versus area. And so what is sea ice extent? It's not actually the same as sea ice area, but something we use in Arctic sea ice research to also describe the areal extent of sea ice cover. But it's a kind of a binary way of counting sea ice, and it basically counts whether there is sea ice or there isn't sea ice in a grid cell. So when there is, if a grid cell is covered by more than 15% of sea ice, then we assume the whole grid cell is covered by ice, even if it's maybe only 85%. If it's less than 15% of ice cover, anywhere between 0 to 14%, then we assume the whole grid cell has no ice. And so that's what extent counts. It counts all the grid cells that have ice versus the ones that don't. And now you might wonder, why do we have something weird like that? That's because of the satellite data. The satellite algorithms have a hard time agreeing specifically on how much ice there is. They're very good at saying whether there is ice, especially if there's ice more than 15% or not. But they have quite some agreement. Is it 80% or is it 70%? There's differences between the different algorithms that are being used. So we can see that here for the area, the different satellite algorithms that have offsets and how much sea ice area there is in March as well as in September. Whereas they agree much, much better on the extent, so whether the grid cell is sea ice covered or not. And so that's kind of how the sea ice extent came along. The problem with it is also it's very sensitive to the grid size, since it's counting the grid size by grid box by grid box. And so in the last decade, people have been moving more towards sea ice area despite the uncertainties in the observations, especially when we're dealing just with models where we don't have that uncertainty. We know perfectly well how much sea ice our model simulates in a given grid cell. And so early on, many predictions were based on extent. Now more and more are based on area, but some are still based on extent. And that has another influence on the predictions of another decade or so. So sea ice extent, for the first time, ice-free in 2038, the same ensemble members before. But if we look at sea ice area from the same model run, then it's already in 2029. And because sea ice area is always less or equal in the perfect case than sea ice extent. And so again, we can get an ice-free Arctic that's 10 years earlier predicted based on the exact same model runs, just using different definitions. And again, that's something that's very clear across all the CMIP6 models. So taking that kind of, keeping that in mind, so some of these predictions are based on sea ice extent, like this paper here, where we looked at the prediction uncertainty, how well can we actually predict an ice-free Arctic? And what we found based on the CSM1 large ensemble at the time was that we have about a 21-year uncertainty of when ice-free conditions in sea ice extent are first reached, based just on internal variability, because all the model runs were forced the exact same way. And that's something that's similar, but even potentially slightly larger uncertainty in some of the other large ensembles that have become available since, with several around 2 decades and then some up to 3 decades. And then this is the first 50 members of the CSM2 large ensemble, which has this weird bimodal distribution because of the biomass burning emission impacts. And so that one is a little out. That has 4 decades, and similar to the Ken ESM2. They go up to 4 decades. And so that shows us that we have a very large internal variability uncertainty. And so unless we can actually predict that internal variability uncertainty better, which we currently cannot, we can't predict the exact year that the Arctic will go ice-free. We can only give a 2 to 3 decade range of when that is possible. We can look at that in the CSM1 large ensemble. And we can see that we have very different trajectories to an ice-free Arctic. In some of them with very rapid ice losses, where we go from kind of present-day conditions to ice-free in less than a decade, and some that have kind of more of a linear up and down kind of evolution. And they're all equally physically possible since they're all based on the same model. What we can also learn from these simulations is that we can reach 1 million square kilometer of sea ice relatively quickly in less than a decade once the sea ice extent is below 3 million square kilometer in the mean, since we can lose up to 2 million square kilometer in these models, not just the CSM1, but also other models year over year, and so we can get there relatively quickly. So far, the minimum was about 3.5, so not quite, but in a couple of years, we could get to the 3 million, then we could be within reach of getting there potentially within a year. The other thing that we can learn from these large ensembles is that we can see rapid ice loss events where we have a very large loss of sea ice in a couple years, especially after they're especially common after periods of reduced sea ice loss, like we've been experiencing now. We see that in several of these ensemble members here. We don't quite get to the 1 million square kilometer, but very, very close. And if we look at it in large ensembles, we actually find that 25% of large ensemble members first go ice-free during a rapid sea ice loss event. So again, doesn't say it means that that has to happen in the future, but it's something that, based on the models, is a possibility that we can get to ice-free conditions relatively fast. So when can these ice-free conditions first happen? Not just based on one model, but like on all the models. So based on the CMIP6 models, and we're going to focus on the selected ones that do reasonably well over the historical period for sea ice, we can see that they have first ice-free conditions happening already prior to 2020 and in the 2020s and 2030s. 66% of them have had ice-free conditions prior to 2050. And so in this IPCC speak, it's likely that ice-free conditions will have occurred by 2050. What we also see here is that the occurrence of a first ice-free Arctic is primarily determined by internal variability once we're close enough in the mean state, rather than scenario differences, because we don't really see any difference in the occurrence of the ice-free conditions between that the SSP 585, which is the strongest forcing, will go ice-free faster than the SSP 119, which is the weaker forcing. We also looked at it in terms of the Paris Protocol goals a couple of years ago to see what that means for the Arctic. And there we found that there's a small 10 to 20% of chance of not seeing an ice-free Arctic at all if global temperatures are kept below 1.5 degrees in the climatological 20-30 year average. That was based on the special IPCC runs with the CSM1. And here bias adjusted for the mean state bias, and so that reduced it to about a 10%. If we revisit that with the CMIP6 models, here the global temperature anomaly is just calculated for 5 years, so not quite as climatological as here, but similar. And we can see again that it's about a 20% chance of not reaching ice-free conditions if warming stays below that 1.5 degree threshold. Whereas if we go to 2 degrees, we're at the very likely. So the difference between 1.5 and 2 degrees in the Arctic is really this shift of potentially avoiding ice-free conditions to basically guaranteed ice-free conditions. And it becomes, it's much, every month it's less and less likely that we can still keep to this 1.5 degree threshold. And so with that, kind of an ice-free Arctic becomes not just a remote possibility that might happen by the end of the century, but something that's potentially going to happen in the next couple of decades and likely to happen by mid-century. However, I think it's really important to point out that future emission choices have a big impact on how the Arctic will actually look like. We might not be able to avoid that the Arctic goes ice-free occasionally, but we can still shape what the Arctic looks like in the later part of the century. And so this is what's showing the probability of ice-free conditions in a given year under these different SSP scenarios. And we can see a very big difference in after mid-century when the forcing impact becomes really clear between the different scenarios where the Arctic is ice-free year after year in September. Most years, like every couple years, we get an ice-free. We get still some ice in the Arctic. And then if we actually, the SSP 119 uses or assumes carbon capture, and so actually bringing temperatures back down, similar to the SSP 126, to a lesser extent. And so when temperatures come back down, then the probability of ice-free conditions in the Arctic go down again, as the ice is a very fast responder in both directions. And so it was one of the canaries in the coal mine of warming and the impact that that has on the climate system. But it's also one part of the climate system that responds very quickly if temperatures were to come down again in the future in terms of regrowing. Since we saw that it has this huge seasonal cycle, and so it grows a lot of ice every year, and so that's not it's different from the Greenland ice sheet where we can't bring that ice back that we're melting. Again, we always focus on September because it's the minimum where we're going to reach ice-free conditions first, where we see the largest changes. But the Arctic actually could potentially go ice-free in other months of the year. And under the worst-case scenario, the SSP 585, which we're hopefully not on track for, but still worthwhile looking at. At the end of the century, it has ice-free conditions for 5 months of the year, year after year. It's 99% chance. And a potential for another 4 months of ice-free conditions, which will bring that to 9 months of ice-free conditions. So more ice-free than ice-covered, and that would obviously be a completely different Arctic than what we have today, or that we would even have under SSP 126, where the Arctic would be ice-free maybe every year or occasionally, and potentially also in months outside of September, but not for more than half the year. And so the warmer it gets, the larger the probability of seeing ice-free conditions in months besides September. Enforcing also impacts how fast this transition goes and which regions become ice-free when. And so that's important for stakeholders in the Arctic, planning in terms of environmental concerns, but also the shipping companies kind of looking at when will the Arctic be accessible. And so we can see, again, very large differences. This is looking at the year of consistent ice-free conditions. So after that, the Arctic should be ice-free in that region consistently in that months of the year. And we can see very big differences between the lower emission scenarios where part of the Arctic will have ice. And we especially see that the ice-free conditions would be limited primarily to the September, whereas in the SSP 245 even, we have basically no ice left during 3 months of the year by the end of the century, and then the full 5 months of no ice under SSP 585. And so for the future of ice prediction, even though I already said we have a lot of definitions, another thing we looked at that we thought it was important now that it's kind of not a remote possibility anymore is to actually also do predictions of ice-free conditions in the daily data, because that's going to be the actual first time that we will see ice-free condition, that we'll have an actual satellite image of an ice-free Arctic rather than a model simulation or artistic rendering. And so we looked at that in the CSM2, and we found the offset between the first ice-free condition in the daily versus the monthly data. This was shown here, and we can see that on average, the offset is 4 years earlier, but the range is really large between some where it happens in the same year, and then the maximum where there's an 18-year offset between the first day where we have ice-free conditions and when we get a whole month of ice-free conditions. And I think, again, that's important to communicate, to kind of set the expectations, because that can obviously happen if it happens 18 years before the monthly ice-free condition, puts it even earlier that ice-free conditions could happen for the first time in the daily data. And that's going to be also what's going to make the news when we have that happen for the first time. In terms of what makes the news, so the CIS community, I think, really needs to grapple with how will we actually decide that we have reached ice-free conditions because of these different definitions that are out there, the uncertainties in the satellite algorithms that we're going to base that call on. We're going to actually base that on satellite data, not on models. And so I think that's something that we need to talk about in the next couple of years to whether we're going to use C as area or C as extent. Again, especially for satellite data, extent model, they agree, the algorithms agree better. Area will happen earlier though. And then which satellite algorithm will be used, because again, there's this offset. Here's about 1 million square kilometer in the summertime. So there will be quite some time between these two, the NASA team and the bootstrap algorithm reaching ice-free conditions. And then we can actually focus, once we have agreed on what definition we're going to use, on predicting expected observations with exact same definitions and actually using satellite emulators to account for these uncertainties in the passive microwave model, passive microwave account for the uncertainties in these algorithms that work on the passive microwave data to predict that potentially better, especially as we're getting into seasonal forecasting regime. So to summarize, the Arctic sea ice is declining due to anthropogenic climate change, and the aerial September sea ice cover already is reduced to about 50% of what it once was. And so it's the canary in the coal mine of climate change. The timing of the first ice-free Arctic will be determined by internal variability. We can't predict the exact year because we have a 2 to 3 decade internal variability uncertainty. Ice-free conditions could occur as early as the late 2020s or 2030s, but could also be delayed until mid-century due to this uncertainty from the internal variability. Only if the warming can be limited to less 1.5 degrees globally is there a small chance to avoid ice-free conditions. Daily ice-free conditions may occur over a decade earlier than monthly mean ice-free conditions, and future greenhouse gas emission choices will determine how frequently and for how many months a year and where in the Arctic we will see ice-free conditions during the century. So, thank you.
Okay. Yes. Go ahead.
Hi. I was just wondering whether if there is any role for oceanic heat release from the Atlantic layer coming into the Arctic, and with all those biases in the Arctic Ocean, and will they impact the initial sort of melting? And you seem to be primarily attributing the whole thing to anthropogenic climate change. Although Atlantic layer changes may have anthropogenic change too.
Yeah, so there's definitely a lot of biases in the models in terms of the Atlantic layer is often too deep. And in general, we do have enough heat in the Arctic, in the Atlantic layer to basically melt the whole Arctic sea ice instantaneously if it could get to the surface. But the Arctic is very strongly stratified. But and we've seen in observations and more in in observational campaigns that, especially in the Nansen Basin in the Arctic, that they have been in recent years only some intrusions of Atlantic water into the surface water. And so that can definitely contribute to the melting. That's also region where already in the summertime we already don't have much ice anymore. And so potentially that kind of limits that because it didn't used to happen. And now cruisers have observed Atlantic layer in the surface. And so potentially that can accelerate it further than the models are predicting. And so yes, I think like if anything, the models have always been a little on the slow end. And so I think it's really important. But now we're getting to the point where it's like the models predict it could happen and this decade, couldn't happen next decade. But again, there's a lot of model uncertainty and that can contribute to that. And we definitely see that also in the Atlantic. And in the Pacific side as well, that ocean heat transport has a big role. And specifically for these rapid ice loss events that Marika worked on as well, but other people are working on as well now, that ocean heat fluxes have a big role to play for these very rapid ice loss events. And so there's been found that some of the rapid ice loss events are Atlantic influenced, ocean heat flux from the Atlantic, and some are Pacific, and some are both. And because you can't melt that much ice just from the atmosphere alone. And so the ocean has a really important role, especially for these rapid ice loss events. And I think there's still a lot that we need to understand there, and then also in terms of the limit of what the models can actually simulate. But even with the limits that they tend to underestimate, that flux is still already simulating these rapid ice loss events that are dependent on Atlantic and Pacific Ocean fluxes.
Thank you.
All right, do we have more questions from the audience? Ayla, go ahead.
So you mentioned that the ice responds very quickly as it cools. Does it go back along that same line as a function of global mean temperature?
Yeah, I don't know if I put that in the supplement, but yeah, basically it's the exact same line in terms of temperature. Yeah, here, I put it in there. So that was a paper from Lee et al. From 2013, where they did a big hysteresis experiment to kind of look at that. Yeah, so it's the same line. In terms of this temperature. Temperature has some delay to the CO2, so if you plot in terms of CO2, you see some delay, but in temperature, it's very, very fast, and so it really goes up and down the same line. And other people have also removed sea ice just in transient simulations. And there they found like it takes about 5 to 7 years to kind of get back to the exact same thickness distribution, everything. Because like in order to get 7-year-old ice, you need 7 years or something, and that's kind of the thickest ice, but that's kind of the time span that it needs. So once we're back at a temperature that supported sea ice before, the sea ice will come back. And so we see that already in this SSP 119, that like after mid-century, the probability of ice-free conditions goes back down.
Right. Yeah. Dave, go ahead. And then...
Well, it's not really a question, but it seems like it could be related to the ocean circulation, right? If the ocean circulation changed some way and the models aren't capturing that, then there could be some more hysteresis.
That could be a
right,
little.
if it's like consistently transporting heat up.
Yeah.
My question was about, you know, the scientific community is gonna have a messaging issue, I think, when it first goes ice-free, and I guess I've been trying to think about what the right message would be, and I guess you've probably thought about it a lot. So just curious what your thinking is to you know, what's the message when it comes ice-free?
Yeah. I mean, I think what's the most important thing for us as CS community to tackle is to kind of agree, and I think like the whole communication, have we already crossed the 1.5 degree, everything's lost, the Paris Protocol is already over. That kind of made me think about that especially seeing these different definitions and like all the uncertainties in the satellite data and the grid size dependence of the extent measure, and if the satellites are going to lower and lower, a higher resolution, all these kind of things. And so I think there it's very important that we kind of get on the same page to kind of, so that it's not like Avi says it's ice-free, but NSIDC says no, or the other way around or something like that. I think that's really important, that like there is, that we have that, and we know that beforehand. We don't just have to scramble one August day when this happens. Like, are we going to call this today or not? But talk about it now, where we probably still have a couple of years. And the other thing I think that's really important is that it's not the end of sea ice. Like it's that sea ice still will come back in the winter for a long time, and that there is still a really big impact that that we have on how the Arctic will look like. Because I think sometimes when it's like, okay, now we've made the ice go away with our emissions, like now that's kind of set. First, the sea ice can come back. Some of the impacts can't be reversed. We're already seeing this coastal erosion. We can't bring the coastline back. Even if we bring the sea ice back, then we can stop more erosion, but we can't bring the land back. So I think that is important, that like sea ice is reversible, but we can't reverse some of the impacts, species that go extinct. But I think it's also really important that we can still save a lot of sea ice and kind of limit ice-free conditions to something that happens occasionally in the Arctic and only maybe in September. And it doesn't have to be something that dominates what the Arctic looks like for 6 months out of the year. But I think it is a challenging communication moment. I think the first thing is really that we need to kind of, now that we see this happening, pretty certain that we kind of really agree on when are we going to call that, and then what's going to be the messaging about that, and refining the projections as much as possible as well.
Yeah, just follow up. I think I agree. It'd be very easy for reporters to write the doom and gloom story.
Yeah.
Right, because it's like, here it is, it's proven, we're all.
Yeah, and I think that's why I mean, I was surprised when I made this figure for the first time back in 2018, and looking at how many months could be ice-free, like even going to this December where it's like pitch black dark in the Arctic, and I would have thought we'd lost all the heat from the ocean, but apparently no, because we put so much in during the summertime. And so I think, like, yeah, it's not binary, right? There's ice for 12 months of the year, and even if we lose it for 1 month, it's a big change that happened, but it's not the end of all sea ice. And I think this message of hope that we can still save a lot of sea ice, I think, is really important, and we can limit how long that ice-free season will be in the Arctic.
And that this was expected.
And I think that's the other important thing, that if we don't get caught off guard and be like, oh, he said it was going to be 2080, and now it happened in the 30s. Yeah, and especially with this long pause now, where we haven't lost any ice, like, makes me really worried that like we're going to be on one of these rapid ice loss scenarios that we see in the models, because that's what often, not always, but often happens in these model runs when they have that plateau. then because the forcing and the internal variability suddenly point the same way, and then you can lose a lot of ice in a very short period of time. Yeah.
So you wrote up that selected CMIP6
Yeah.
models. So how did you select them?
Yeah, so this one is based on, so that's another thing we need to grapple with that I didn't include today, but there's many different ways to subset models for all applications, but also for CIs. Here we went with, what we came up with for the CI's modeling intercomparison project, where it was based on the response, the CI sensitivity to CO2 over the historical period, so the model that we're within internal variability uncertainty of the ice loss over the historical period, and we're within the internal variability uncertainty of the mean state in March and September, so that they kind of get the right mean extent, so they don't start at 15 million square kilometer and they're not already at 2 million square kilometer in 2015, basically. So that was the two criteria that we used here to kind of narrow it down into a subset of all of the available ones.
So did that eliminate many models or just a few?
Quite a few. I don't know the exact numbers anymore. Might say on this figure here from the Alexandra paper. Sorry. Oh, here it is. Okay. This is the number of models so that were run. So we for one of them for the SSP26 we went from 67 to 33, so about half, and similar for the other ones as you can see. So it's about half that got eliminated was the selected one, and especially there were a lot. There was and it's at both ends that kind of were eliminated, as you can see here. So some that were ice-free already prior to 2010, and then the top number here says how many were not ice-free by the end of the century, and so most of those got eliminated as well because they were still at CS extents of like 14,000 million square kilometer in September or something. So obviously they take a longer time to then get to 1 million square kilometer. But that's not the only way, so there's been many different ways that's been tried to kind of select which are the best models. Also many efforts to do model recalibration and sometimes they worked in opposite ways. So last year there were 2 papers that recalibrated when an Arctic will go ice-free, and one found that it would be 10 years earlier and the other found that it would be 10 years later based on different ways of recalibrating the climate models. And so that's the other part that I didn't talk about today because I figured maybe that's not so much of interest to people here, but something that we I think need to grapple with and kind of better, like do an actual intercomparison to better understand what the impact of these different choices is, and because they all use different underlying data sets, so you can't really say exactly, like, would this work on the exact same data set, would we see the exact same response or not? And yeah, so I think that's the other part that kind of goes into, we need to refine predictions, and in order to do that, we need to better understand these different refinement and model selection methods.
Yeah, go ahead.
During that period of ice area plateau, does volume continue to decline? And if so, does that give you some predictability of when you would leave that plateau?
Yeah, that's a really good question. Initially, it declined a little bit, but then it's also leveled off in the last couple of years. And so, so it's really just kind of been a pause in sea ice, and it's different. People think it's more the ocean, some people think it's more the atmosphere. Probably it's both, because they both influence the sea ice. But that's kind of what there's like 2 big papers on it. One was all the atmosphere, one was it's all the ocean. That probably, both of them are probably right. And so that's going to be the 3rd paper that hopefully someone writes. But yeah, so it actually has led to kind of a pause in the sea ice loss. But yeah, that's another really important part, that sea ice isn't just a 2D quantity, it's a 3D quantity. We just haven't had observations as long. But we had them over the last decade, and they've been relatively flat as well. And if anything, we've had some more loss in the winter thickness, but it's not been as drastic as it was in the 2000 to 2012 period of time. So it's really been a pause.
Okay, one last question. Go ahead.
since the area is always like less than the extent, have you considered using a different threshold to define ice-free Arctic to reconciliate essentially the time when that's going to happen, your prediction, when you use one or the other?
Yeah, to kind of align the two of them, yeah. Yeah, I haven't looked at that. That was something that, we've thought about too, kind of, but it's just, the 1 million square kilometer kind of was something the community agreed on in 2009, and then because it was like, well, it is virtually ice-free for most purposes, and then people just started using it both with extended area, and so they're both already out there in a way. And the tricky part, I tried playing with that to kind of finding the equivalent, but since the extent is so sensitive to the grid size, like, so if you're just changing that, then different numbers correspond to the same area, and so that's kind of the tricky part. The area is, like, it doesn't matter what your grid resolution is, but extent changes depending on what your grid resolution is, and so you can't really find it like, just like, okay, let's just move this up, it's like 0.7 for area is the same as 1 million square kilometer for extent, because the extent one varies, and so area, I think area is the better one because it's not dependent on resolution. But again, since we have to detect it with the satellites, and so I think it's really important that we have uncertainties on that, that we have a better understanding of what the uncertainties are there, and kind of work on predicting the specific sensors, basically, of when they're going to see ice-free conditions. And again, nothing magical. And I think that's the other part about the communications, it's not zero, but even zero, nothing magical happens. It's a transition. It's the end of this transition towards ice-free conditions in a given month, but it's like the impacts are the same at 1.1 or 0.9. So in a way, it's kind of not. Yeah, it's a tricky thing to deal with these thresholds, and especially when they're not absolute. So. And if anyone has great ideas on how to talk about that, just people, I'd be happy to talk about that more offline.
We are right on time, so let's thank our speaker again. Yeah, if you have other questions, just, yeah.